Fernando Lucatelli Nunes, one of my PhD students.
Good morning, my name is Fernando Lucatelli Nunes. I work currently as a PhD student under Matthijs Vákár at Utrecht University. My background is in category theory. I'm currently mostly working in programming language semantics, especially in categorical semantics for programming languages. The subject of this talk is automatic differentiation. So of course we know that there are many situations where we want to compute the derivative of functions, especially underneath machine learning, generally optimization and scientific computing. The definitive solution for these problems are usually related to compute the derivatives manually, but this can be a hassle if you're prototyping, so we want a system where we don't need to compute a custom derivative for each prototype. So this is where the dream of differential programming begins. We want a programming language at DSL with support for differentiation. Of course, we want it to be correct. We want to compute at compile time, and we want complexity guarantees. In the practical cases, the functions have domains with large dimension, and because of that, we usually care more about the so-called reverse automatic differentiation. It exploits the chain rule to compute the derivative of functions. It gives numerical stability, and it computes the transpose of the derivative directly, and that's precisely good when you have a function with a domain with large dimension. For expressive total languages, we achieve this with the macro we called CHAD, but our past work does not support partial features. And we want partial features. In particular, we want iteration, especially because some functions are computed as Taylor approximations, especially the gamma function. So we need, or at least we want, at least CHAD for iteration. Let's firstly recall why do we care about CHAD. Firstly, the denotation semantics of the reverse mode is simple and elegant. The proof that is a denotational correctness proof, and it follows almost directly by logical relations argument, and the denotation semantics is actually close to the actual implementation compared to other paradigms. And finally, it's a good candidate to exploit parallelism in the future work. So CHAD is realized as a programming language transformation. So we have a source language and a parallel language. We write our program in the source language, and then we want this translation to have both the original program and the derivative next to it. We achieve CHAD by exploiting this perspective that programming languages can be seen as freely generated categorical structures. And with this perspective, we achieve the definition of CHAD by universal property, as well as the concrete semantics and even the correctness proof. So these three are actually functors that preserve structure, and they are uniquely defined by the universal property of these freely generated categorical structures. But in order to really follow this perspective, in order to get all these things as the uniquely defined functors preserving some structure, we need to have enough structure in our target language. In particular, for the general case, we need linear types, and if you want variant types, we need dependent types on our target language. The concrete semantics of this target language is this category fun vect op. We are going to talk more about this category now. So let's talk about the denotation semantics of the target language. This is the category fun vect op. It's just the free completion on the crop products of the dual of the category of vector spaces and linear transformations. If you don't know that, what is this? I will give the explicit definition. The objects are pairs of a set and a family of vector spaces. You can think as a space and the family of tangents for each point of this space. And morphisms are functions between the spaces and a family of linear transformations. And again, you can think of this family as the family of the transposed derivatives of the original function. The composition is actually given as what we expect, by which I mean the chain rule. It's basically what you expect to be the general chain rule. And this is actually the first step of the correctness proof. So giving two pairs, f prime, g prime, where f prime actually gives the family of derivatives of f, and g prime gives actually the family of derivatives of g, the composition in this category actually gives the composition of the functions and the derivative of this composition. But of course the correctness proof goes beyond. It shows that you can use this structure of the category and you are going to still get a correct pair, a pair where we have a function and its derivative, by which I mean we can use the universal property of coproducts, products, inductive types, and so on, and exponentials, and as long as you started with a set of correct pairs, where we have a function and its family of derivatives, we are going to end up with a correct pair. And this gives the correctness proof, basically, of CHED for expressive total languages. But funvect op does not support partial features, and we want partial features. So the first and the most natural thing to do is to consider p funvect op, which is just a Kleisli category of funvect op with respect to the monad plus terminal. If you don't know what it is, I can give you the explicit definition, which is the objects are the same as funvect op, so they are pairs of space and something that plays the role of a family of tangents, and the morphisms are now pairs of a partially defined function and a family of linear transformations, again, which plays the role of the transpose of the derivatives. We have this catch, which is the tangent of undefined is defined to be the vector space 0, the vector space with no non-trivial vector. Hence, what we are actually doing here is saying that the derivative of f and at a point where it's not defined is 0. Again, the composition is still given by the usual chain rule, which is of course needed to get the correctness proof. And the fun thing is, of course, the p funvect op supports partially defined functions as defined, but besides that it has a natural notion of iteration provided by this natural notion of omega CPO enrichment. And now the correctness is basically saying that we, starting with a function with a pair with a function and the family of derivatives in this category, we have this natural notion of iteration in this category and can apply it, and the resulting thing is a correct pair as long as the starting thing is a correct pair. By correct pair I mean a function with paired with its derivatives. So what we are basically doing is we start with a function from a to space a to a plus b, and we consider we assume that it's differentiable, and then we consider the iteration of this function, and we can prove that it's differentiable, but this is actually a calculus exercise. But what it means that if f is defined in in a point in domain, that actually there is k such that fkx is equal to the iteration of fk, and what we do in this case is the chain rule. The category already takes care of that, and if f is not defined in a, or if iteration of f is not defined in a, then the derivative never gets out of 0, it will be 0. Yeah, so if you have any more questions, maybe you can reach me. Thank you very much for your time. Sorry I couldn't be there, and thank you again for this opportunity.